Alrighty, we are live at the 67th annual SPWLA Symposium at Lake Conroe, where petrophysicists, well log analysts, wireline servicing, it's all coming together, it's all integrating around the wellbore. It's where engineers and geologists and CEOs, it's all about what's happening at the wellbore, what data do we have and information do we have that tells us this is going to be a commercial hydrocarbon and this is going to be a commercial oil making well. Please introduce yourself. We're in the poster presentation session of day 2. Please introduce yourself, tell us about yourself and this poster.
Okay, thank you. My name's Brendon Negenman. I'm a geophysicist by background. So I work mostly on borehole seismic data, but I've started to work more now on this kind of data. So bring in some of those skills and kind of different viewpoints.
Yeah. And who do you work for?
I work for Halliburton.
Oh, nice.
Yeah.
Big Red.
Big Red, yeah.
How long have you been there?
I think about 13 years. 13 years. Yes.
Wow. Okay, so what's the poster all about?
Okay, so the poster is it's a case study, and it's using the dipole sonic data, and it's really to estimate the dips. This is for a deviated well. So this is showing an example. So we have a deviated well geometry, and for example, this is a formation, and then you're going to get reflections which are going to be above and below the formation. This is a wireline tool. So we have 13 receiver array, and we're using dipole sources. And one thing to highlight is that this is going to give an uplift in resolution compared to surface seismic because the frequencies are so high. You can see here about 1 to 3 kilohertz. So I'll just go through this is going through the method. So we have figure 2 here, which is it's showing an overview of the processing flow. And the idea is that you want to remove this direct wave, which is a source of noise, and you want to highlight these the reflections. So what we're showing here on figure 1. And once you have those reflections, this is a new method that was developed by Mark Willis. He calls it the velocity scan. And so you look at the move out of the reflections to get an idea of the apparent velocities. And apparent velocities can tell you more about the wave types and also can be used to estimate zones of interest, because this data can be difficult to interpret. So what we do is we process the data. So we're removing this direct wave here.
This is how the data looks when you get it back from the wireline?
No. This still has some filtering applied. So this represents a single receiver, and you have time here, and you have measured depth. So this is the direct wave. This is the wave that's not a reflection. It's traveling along the borehole. So this is a source of noise that we need to remove. So you can see that this is removed by this filter. And what we want to focus on are these upgoing and downgoing reflections. So you can see we have these lines here. And so we look at this velocity scan. What that's going to do is help to identify interesting zones. So from this analysis here, we have this. This is the apparent velocity result. So you have measured depth here, and then the apparent velocity. So you see this large red amplitude. This corresponds to these reflections here. And one thing to highlight is that you expect the reflections to have a higher apparent velocity. So this white line is the velocity at the well, and then it calculates different scenarios for different formation dip. So you have 70 degrees, which is the maximum. So we can see that this red range is in between about 50 to 60 degrees, and that makes sense considering this is a deviated well, and you expect the formations to be quite gentle. So from this, we then build our velocity model, which is shown here. And we're using a flat velocity model, which it gives a pretty good fit. So this is our migrated image here. This represents like an ultrasound. You can see that these are boundaries. We're going to have a change in the impedance. So it's the velocity and the density. You can see this horizon here. And the idea is then to calculate the dip from this image. So that's what this is shown here. So the target, which was here, is this one, which is about 3 to 5 degrees. So we have good confidence what this dip is, and it's about 50, 60 feet away from the wellbore. So we're comparing that with our borehole log, which is just a local measurement and also has some uncertainty on the value. So we have 2 to 20 degrees coming from this log, and then using this migrated image, we have more confidence that the dip is about 5 degrees. So it's just a way to quantify your borehole geology interpretation.
It's reading out, how far did you say it was reading out of the wellbore?
So you can see here, this is a scale. This 0 is reference to the wellhead, and so this is the wellbore here, so that's about 50 feet, maybe a little bit more. You lose some of the data quality, but it looks definitely much further than a typical logging tool. Yeah.
Great. Thank you so much for presenting. Thank you for being a part of this show, and good luck with everything at Halliburton that you guys are working on.